apply at the top the load, right? These are known as PY springs. You apply the load and you find out the bending moment, right? Remember, there are two main things: free head pile, fixed head pile. So this example of fixed head pile, fixed head pile, you know what it means? There is bending moment at the top of the pile. Fixed head means there is bending moment there. So the bending moment for this pile, if I draw the bending moment diagram, this will be like that. That's the bending moment diagram. So you will have some large bending moment is at the top, right? And that means you will have a very good reinforcement there. If it is this particular case, free head, the bending moment would be like that, 0 at the top. Okay? So by this model, you can find out the bending moment in the top. Okay? There's a no leaky surface. Suppose soil liquefies, and if it actually it liquefies up to that level. So your model becomes, you simply erase these springs, right? You erase as soil liquefies to that level. That means there is no lateral spring. Okay? And you then also put the vertical load here, and it doesn't buckle in that unsupported. Yeah? It should not buckle because we got a vertical load there. This unsupported length, check against up. Yeah? So you will check against bending due to inertia, then check buckling with unsupported length. You check against 1 plus 2 bending buckling interaction, right? Because when you have a buckling problem, the load will reduce because now it's a more flexible system. You check against this condition. What else can happen? If you lose the shaft resistance there, the pile may settle, right? You check against that. That's called settlement. Okay. If it is a concrete hollow pile, means very low in shear capacity, you check against the shear, right? So 5 is shear. And lastly, suppose the ground is sloping, it gives lateral load. You check against lateral spread. But if the ground is sloping, the soil will flow at a lateral load, right? You check against that. And then you can check against the combination. Think about scenario. What can happen to that particular place? What are the loads? Right? So you can think about the different load cases for the whole life of the bridge. Right?
The effective length it would be just
Yes.
two layers, right?
Yeah. So effective will be, suppose this is your bottom of the digging of a layer. You take a fixed leader. So then the effective length would be there, slightly down there. So suppose this is 10 meter and the pile is say 300 millimeter, 300. So this will be roughly 10 plus 0.9 meters. So 3D you can take as the one to fix it. Fix it here. If the top is restraining the rotation or not. If it is rotation, if you can rotate, the effective length would be twice this. If If it is there, you do boundary conditions. Okay. Now, up to here, the file is unsupported. But the fixity will be set deeper. And this fixity is normally 3 to 5 times pi diameter. So, at deeper depth, you can get 3 diameter. Yeah?
If it's fixed, I'm picking the 0.7.
Yeah, so you can use the theoretical values, the theoretical estimates. I think in the class what I did before. So main thing is to find out the equivalent pin-ended strut. So what you do, so again it's effective length concept. So that means suppose that is the bottom of liquefiable layer. Bottom. And that's down low. This is yeah. And say in one case you had the pile down here and it's slightly embedded here, slightly, right? And you have the building, the top of the pile cannot rotate. So it would deform in this way. So the earlier the load was there, now the load is there. Okay? This is pinned and pinned. In this case, the effective length is twice F. Because the trick is you find out the equivalent pin-ended strut. That means if you look into that is the original Euler formula is for this thing. Yeah? If you get now fixed, that means fixed and fixed. How do you get half? So it would deform in this way, right? So what you get here, you can see this part is a cantilever. This is a cantilever. Actually, this is pinned from there. Again, that is cantilever, pinned there. That is the effective length. So this is 0.5 times L. That's why it's half. Okay. In this case, you can get equivalent that if you extend that there, then that becomes 2L. Right? If you can get a case where it goes down here, but the top can rotate, effective length will give you like that. Right? Then the effective length becomes you extend 2L. Okay? So you think about the construction of geometry and then you can work it out yourself. You don't have to remember what 0.7, 0.8, 0.9, just keep it in there. Yeah?
What is the difference between the first one?
So basically, if you look into the Euler formula, the Euler P critical is given by pi squared EI by L effective square, right? The codes give you L effective. For a fixed case, you now use 0.5. Yeah, isn't it? For a fixed case. For cantilever, L is 2L. 2L. So this is how we get this quickly, these lengths form. Yeah? This may be slightly beyond the this is a structure first mechanism. That's it? Okay. Anything else? I think this is the end of the what I wanted to teach in this course. So start from the hazard to design. So all this sort of more or less.
Shivi, when you have, imagine that, and you had a liquefied layer on the top, and then a non-liquefied layer, and another liquefied layer, would all of it act as a liquefied layer, or not?
Well, okay, now the main thing is that will that layer stop it from deforming? What's the
Yeah.
what the main thing is what when we say fixing is what is not letting it move. If you have a liquefied layer and the top a big liquefied layer, the top is not liquefied layer. Of course, the pine wants to move. It will push those things someday. So the load what you calculate will be a bit more higher, but still will be back. Isn't it? If you're thinking about it, we are thinking about fixing it. Can it stop it from buckling? That's the question you asked. Will that non-liquefied little part will stop it from buckling? Can it? Or can it? Now what happened in reality? We have a liquefied soil. The top is not even rust. It will start to settle because this soil can't take the load. So that top part will start to crumble down. Think about it, like a middle part suddenly is like a mud. Suddenly, it's safe to use bottom liquefied line. That is the answer.
So if you had a liquefied layer, a non-liquefied layer,
Yeah.
and then another liquefied layer,
Yeah.
where do you draw the line between if that non-liquefied layer becomes liquefied because it's sandwiched between
It's not I would say non-liquefied, but it can't give support against, can't provide support against that.
So you treat it would be sort of the same as if all of that liquefied.
Effectively that. Yeah, effectively that. Isn't it? Effectively it is like that. It's a quite a hard topic.
Yeah.
Quite. You see, still here you see every year I'm giving things to how things fail. And it's quite difficult.
So if we have defined our numbers,
Or the answer is answerable. Mean to say it's answerable. So another way to do this because what's happening? If you have a layer, so that's unsupported load. The non-liquefied layer will then so they have got
Drugs in here.
non-liquefied. So
I'll
the
get a
solid
nice
liquefied
little
underneath.
powder at the bottom. That will really fight. No, I didn't like that.
And if it's settled, so the pile there will be gap form.
When you
If I
accidentally
want
just
to
sweep the last
deform,
bit.
that can't stop it from deforming. Okay. Give me some sort of resistance. It is like
I tried
you
pouring
have
like the
you
last
have
little bit through a coffee filter to like
Yeah, you
still
have
gets this.
needle,
so fine.
Yeah, it just
Needle,
goes
right?
straight through a coffee filter.
and you put it into a jar of sort of fluid, like thick fluid, like diesel, right? And you put some wood, floating wood in that diesel, and you try to push the thing. Suppose if it buckles in air at say 5 kg, and you put it in the fluid, will it buckle at 5 kg or more or less? Same. You can't stop it. And if you put some wood, you assemble or different. What happened? Not assemble. But suppose you have buckle, you find the wood, you push the wood, so it will slow down. The buckling won't be that fast. Isn't it? See, in air, it will buckle immediately, and then it will take some time to it will stop, slow down, and push around. Yeah. So the question to ask: can it stop it from deforming? If it not,
So in this situation here, then, would you assume that it's liquefied all the way down to here, even though there's a massive... Because it... Yeah.
so what happens is that say for example here, right?
Yeah.
So if it liquefies, this is simply
Yeah. And then... Yeah.
and then this
And
will
then
go
like...
get
all this
settled
will
down.
support it.
Yeah.
So So then maybe
It becomes a, and in this case, we will do a model. We will do a model. We will do a spin model to see what load. Then you start to do it because if you actually this whole is supported, massive pile, massive. If I reduce the cost, I said, let us see if you can do it. Or you might try to do here, maybe inflate a file there, do something to set the file.
yeah.
Or try to make the ground improve the ground, do various things. You often get a pretty insight like that.
Yeah. So if there is a liquefy below, then non-liquefy below will normally just settle.
Because that can't take the load. So it can't be the top load. What do you do? Stop. But it's very difficult to handle. You often get those kind of situations. Okay, is there any other question? Otherwise, yes. Liberty cost.
And then on the support, basically lost this much support in terms of fixing it. So your buckling in terms of stuff like that, which isn't all it is that just sure.
Well, the thing to ask, question to ask is, will non-lens material can stop it from deforming?
As long as it's settled.
That's the whole point. Yeah. So you can ask that. If you can't answer it, because these are simple situations. In those cases, then you start to do patterns. Then you can't do a hack, really. Because if you have a hack, you will assume that unsupported. Massive.
But then
There is a lot of cost. Let us now do a bit more deep analysis. Let us do a model. In this case, you can't do a spin model. Spin model against it. Then you go on to experiment. You model the whole thing. Domain by domain, pull down this pockets of these lenses. See how then it becomes expensive. Okay, is there any other questions? Now, we part release this is that. In that decline, what does it mean? That can't take any vertical load. What will this top thing will do? So see, you get a nickel layer, like a fluid. On the top you have a heavy thing. That is like this. Settle down. When once you settle, you start to see gap forming here. Yeah. But if you see any no, so it will settle down. So you will see that it is settled down. There is cracks forming. No. If the pile wants to buckle.
No.
But can that layer stop it from buckling? But that thing is lump mass is going down. Can that stop? It can't stop. Therefore, you have to take this as unsupported. So in that case, in that case, that what is this? Small defect? No. So what I would say is here. And the top part can move laterally or many piles or one low pile or many low pile. So top part floating.
Yeah, if I might be that's
Here is
I don't want my dog, so I just want my
I'd never look at that anyway. But would it mean that if you did do that,
The thing is that you have this layer, if you don't want
if you did that far right,
I want to doesn't want to.
Yeah, I can't time.
Because you can't fall, because there is soil around.
you started earlier, like I told you to start earlier.
Well, what is it?
Yeah, you went to Italy.
Yeah.
But it can't fall.
Yeah, like, I went home from the sort of family.
Pushing the soil around,
That's when I did my
but it can't stop it from
So I did, yeah, it's kind of
Someone like that,
Instead of pushing, it stood up.
yeah.
In fact, we push.
The last 2 weeks that I did, first 2 weeks. Yeah, I didn't know. No, we'll be alright.
The building top what you do. Can that be a stop?
The thing is, like, I mean, this is 5 years ago.
Buckling is unstable.
I just wish I just
Starts to become unstable.
just never. I've started the structure 2 months ago.
What is the offer?
Now that
So once it starts to buckle, it starts to.
there'll be no stress.
Will you stress makes you work better?
No, it
Does.
Because it
fear of failure spurs me.
it is fixed in place. Not getting fixed in place.
Mine's just, I want to get it done.
Have you done the group?
Group.
The
Like half of it.
the
That should be alright. Is that 2 of them? Yeah. Bridge is done there. I just need to write it out. I've got a nice little spreadsheet. The steel and composite bridge design. I swapped from long span bridges to steel.
What one's longer?
I think it.
Oh wait,
Do you
wait, have you got
No.
Oh no, I mean of course it's this is structured earthquake and the steel composite.
So one final point here.
Oh, steel composite is pretty straightforward. Yeah.
Tell me what.
But Jack,
And
yeah.
What will you be doing at research?
So one last final point
that's in like 4 or 5 days.
is
I did that with the college. Alright, I'll see you at graduation.
say from here to here, it is liquefiable there, right? So you can find out the friction in a pipe by, if you know the vertical stress in the ground, sigma V dash, you can find out the lateral stress, you multiply by K, pressure coefficient, sigma V dash, and this is the friction you can find out by multiplying, so K sigma V dash times tan of delta, where tan delta is the friction pile in the soil, right? And the whole friction in this part, pi diameter times this length, yeah? When it liquefies, sigma V dash is 0 by definition, because it is liquefaction. So this becomes 0, so you lose the friction, yeah? So, how do you compute the settlement? Yeah? So, a simple model can be, so you know the vertical load that coming from your structure. This part you assume still offering friction. So, I represent this by a TZ spring. And this part is liquefiable. So up to here there is no springs here. And then you have TZ springs. And bottom there will be an end bearing spring. That's called QZ spring. Yeah? And what you do two analysis. In one, you have TZ spring all along the pile. You find out settlement. Another case, you remove this spring, find out settlement. Yeah? Okay, now, in engineering practice, because you can, normally you don't design piles with finite element, means fully continuum, you don't do it, very expensive. Because you need a 3D software and hundreds of parameters, it's very, very difficult to, unless you are required. So piles are designed with a thing called PY, TZ, QZ approach. So what the approach is? So you split the pile into many elements, and then you model the lateral interaction by a PY spring. Okay? And this you model by something called a QZ spring. This is PY. And the axial by something called TZ. So you basically TZ. Okay, and then you put the load here. You put the load, you put all the loads there, and you analyze it. Now, the part where it liquefies, you simply take out those TZ springs from there. And how do you get the TZ springs? That's the concept. The concept is, suppose here is a pile, and I'm taking this small element and looking into a bit more detail. So here is that particular section. Yeah. So for this section, you can find out the friction given there. That friction of what I calculated there, which will be sigma v dash times k times tan of delta angular friction times this area, right? So pi times diameter times this distance z, or whatever, you know, let's name it L, pi d L. You agree? Yeah. So when you put numbers to it, you can get the force. What does it mean? That means that's a maximum friction that thing can give. Yeah. So once that force exceeded, you basically fully mobilize the whole thing, right? Now, this is the pile cylinder surrounded by sand. So suppose you get, for a particular example, and suppose you get say 20 kilonewton, you get, right? A TZ curve will look like this. This is 20 kilonewton, and this will be 2.5 millimeter. That means if the pile slips 2.5 millimeter, you mobilize fully 20 km. If it mobilizes less, you mobilize less. So this is the way how you can sort of calculate those different springs. And QZ is, you can also calculate that. So once you know the end bearing of the pipe, right? So that will be like NQ times sigma v dash, right? Say the end bearing number is 1 meganewton. So QZ spring looks like that. So this is 1 meganewton of load, 1 meganewton, and you mobilize fully at 10% pile diameter. So the pile is say 600 millimeter, mobilize this at 60 millimeter distance. So you give that curve, you do the analysis, we can put the load. Once you put the load and you put all the springs, you can see what the forces are in each spring. Once you take those springs out, you will see you are mobilizing a lot more end bearings and more settlement. Yeah? So what you are doing, you are transferring load from towards the bottom part of the pile. So earlier, the vertical load was taken by the top part of the pile mostly. Bottom was seeing only 10% load, the end bearing. Right? So if you put the pile here and if you have a load cell, you will see a lot less load. But once you take out the friction there, it will settle, it will take a lot more load. Now if you exceed this 60 millimeter, you fail. Yeah? So this way you can compute the settlement. Yes? Any other question? But obviously not everything can be covered in this course. That's not the purpose of the class.
So, the tip of the pipe, one of the solid code is the water force versus the glass, the active steps of the
What it can take, it is an end bearing, is similar like a footing in ground. So if you have circular footing in the soil, how much it can take? Like CNC have gone bend down, that's the end bearing. Yeah. If there is nothing else, so we will end the lecture there. Okay. Now, thing is, for exam, it is pretty much like previous year's really, isn't it? So, but if you do the coursework, you should be able to do your exam. More or less. Yeah.
Yeah, there's one to that.
Oh, really? Okay. So that's actually an exact
My minute, but I gave you the earlier thing there. Not so many. More reading. More learning.
We did smash it.
But I thought
You're on your own.
maybe
Shit. Probably that. 65. It's just lower than everything. Yeah, no, it's just lower than everything else.
What was that?
MDDP. Yeah, so
Double one.
listen.